I'm Eric Crable, a technical marketing engineer at Xilinx. Thank you for joining me on this quick sprint through one facet of UltraScale Plus FPGA security. This video builds on another video titled Lock Before You Leave. If you haven't seen that video, I encourage you to watch it before this video. In the Lock Before You Leave video, I established UltraScale Plus FPGA bitstream encryption using AES and eFuse is free and easy. I hope you agree there's no reason to leave your design front door unlocked, and that you are alert to the possibility of attack by an adversary. Today, we're going to look at a method to further increase the design security provided by bitstream encryption using additional security features that are included for free in every UltraScale Plus FPGA. Differential power analysis, or DPA, is a side-channel attack, a type of attack based on information gained from implementation of a system versus brute force or algorithm weakness. By monitoring and recording many samples of the power profile of a device or its electromagnetic emission, an adversary can use statistical and signal processing techniques to extract a secret, such as an AES key. There are a number of techniques to mitigate against DPA attack, such as using balanced circuits to minimize measurable swings in power or emission, or adding noise to raise the noise floor for measurements. The approach Xilinx has taken is to limit the amount of data an adversary can collect. This prevents the adversary from performing the needed analysis on the side channel information. DPA attacks generally come in two forms. The first is a random data attack, where the adversary pumps random data into the cryptographic system in order to collect enough side channel information to extract the secret, which in this case is the AES key. The AES key is, for practical purposes, unobservable where stored in eFuse, but signal processing on sufficient side channel information can potentially reveal the key value. The second is a good data attack. Given the size of bit streams, an adversary may be able to use a valid bit stream as input to the cryptographic system and collect enough side channel information in order to perform their analysis. We must consider both these types of attacks in order to protect against an adversary. To protect against a random data attack, enable public key asymmetric authentication prior to decryption, implemented with RSA 2048 and an eFuse key. With this enabled, only authorized bit streams are allowed to run through the cryptographic system. To protect against a good data attack, enable key rolling, which is a technique to break up the bit stream into smaller blocks, each encrypted with its own AES key. There's flexibility in the block size, and only the first key needs to be stored in eFuse. Subsequent keys are protected or wrapped in the previous blocks. To support these DPA countermeasures, we'll need to generate a number of keys. One tool for key generation is OpenSSL, which you can find at the OpenSSL project website. The website contains a wealth of information and provides links to other websites hosting precompiled binaries for a variety of operating systems. You don't need to use OpenSSL, it's just one option available to you. For authentication, we're going to need a public key and a private key. For encryption, we're going to need multiple keys, perhaps lots of them, depending on how often we elect to roll the key. OpenSSL can generate all these keys. Let's see how to do it. To create the RSA private key, use the OpenSSL GenRSA application. I've put a link to the documentation for this application, and below the link is a sample invocation to capture the output into a PEM file. Once you have the private key, you can extract the RSA public key using the OpenSSL RSA application. As before, there's a link to the documentation and a sample invocation to capture the output in a text file. Finally, for AES keys, you can create as many as you like by repeated invocation of the OpenSSL ENC application. Although the invocation shown uses a constant passphrase, it also uses a salt, so each time you run it, you should get a random result. In the Lock Before You Leave video, I showed the specification of the single AES key interactively through Vivado. This set a property in the XDC file, and during write bitstream, an NKY file was generated. Now that we have many more keys, interactive specification is not practical, but we can capture all the key values in an NKY file and use that as an input to write bitstream. Here, I'm showing a template for making an NKY file for the XCKU9P device. All you need to do is adjust your target device and then deposit the generated key values into this template. For authentication, RSA public key modulus is the modulus data block you'll find in myrsa.txt. Then, for encryption, each numbered key and start IV pair can be populated from the output of a key generation run by looking in myaes.txt. How many encryption keys do you need? Well, it depends on the bitstream size and the desired block size for key rolling. We'll look at this consideration in a moment. I won't dwell on this slide, but let's take a quick look at a sample NKY file. Notice I've got line wrap turned on. Each value here is a single string uninterrupted by spaces or new lines. After setting up a project and running the design flow through the implementation step, you can access the full set of bitstream settings by opening the implemented design and clicking Bitstream Settings in the Flow Navigator. This opens a window to adjust settings with an initial focus on output file types. Click Configure Additional Bitstream Settings to open another window for the additional settings. Look at the Encryption Settings group. Enable bitstream encryption and set the location of the encryption key to eFuse. Then, show Vivado where to find the input NKY file you created and specify the key rolling block size in terms of configuration frames. Configuration frames are about 3 kilobit in UltraScale Plus devices and about 4 kilobit in UltraScale devices. The block size needs to be a multiple of 4 configuration frames and must also be greater than or equal to 8. You can find the configuration frame count for a given device in UG570, the UltraScale Architecture Configuration User Guide. Without resorting to math, I can tell you the XCKU9P device I'm using has tens of thousands of frames, so you might wonder how could this work if my NKY file only has 2 encryption keys. If you haven't provided enough keys, Vivado will generate more keys on your behalf and ultimately report them back to you through the output NKY file. However, Xilinx recommends you always generate a complete set of your own keys. Now look at the Authentication Settings group. Enable bitstream authentication and then show Vivado where to find the input PEM file you created. After this, we're done with the additional bitstream settings. You'd click through 2 OK buttons to keep the modifications, save the properties, and close the implemented design. You then click Generate Bitstream in the Flow Navigator. If the design run is out of date, accept the offer to rerun any prior steps. Provided you haven't changed the GUI settings, when bitstream generation completes, Vivado guides you to generate a memory configuration file. Alternatively, you can do it by clicking Generate Memory Configuration File in the Tools menu. During bitstream generation, an output NKY file is created. This file is used to supply data for eFuse programming. What actually gets programmed into the eFuse is the RSA public key digest and the initial AES secret key. If you didn't provide enough encryption keys in your input NKY file for the requested key rolling block size, you'll find the additional keys generated by Vivado in this file. I abridged this for presentation because it contains more than 7,000 encryption keys. The first 2 are from me, and the rest were generated for me by Vivado. As mentioned in the Lock Before You Leave video, if you're using Vivado for both the eFuse programming and the flash programming, it's critical you complete the necessary steps for flash programming before you program the eFuse. I demonstrated programming with flash and eFuse in that video, and here the process is nearly identical, but a few eFuse settings are different. In the eFuse programming key setup, the output NKY file from write bitstream is used to set the key values, and those values must be checked to enable programming as shown. I'm not showing the application-specific eFuse settings page as it's not relevant to authentication or encryption. Further, I'm not showing the control register settings page. As before, if you don't want an adversary to play with your settings, it's prudent to disable all of these, except perhaps the application-specific user fields. The subsequent page, which I am showing, is the security register settings. Config AES only, when programmed, only allows encrypted bit streams, thereby blocking use of unencrypted bit streams. eFuse key only, when programmed, selects the key sources coming from eFuse only. RSA auth, when programmed, enables RSA authentication. All three of these must be checked. You might consider also checking scan disable to disable JTAG access to the device, and you typically leave crypt disable unchecked. Now you've seen how to enable DPA countermeasures to protect against attacks on AES bitstream encryption. These countermeasures are included in all UltraScale Plus FPGAs and are free and easy to use with eFuse keys. What we looked at today can also be used with UltraScale FPGAs in certain configuration modes. These DPA countermeasures are a great next step in better protecting your design, and I encourage you to consider using them in your next design. Thanks for spending your time with me.